All right, let's talk about isotopes. We've learned what happens when you vary the number of protons in an atom, you get a different element. When you vary the number of electrons, you get an ion of that element. What happens if you vary the number of neutrons? Well, you're going to end up with different isotopes of that element. I'll start with an example of lithium. I'm going to draw two lithium atoms. I'll draw left and right, and I'll draw the nucleus very, very large. So I'm going to draw here 6 really large circles, and I'm drawing them pretty large because I want to label these as either protons or neutrons, and I'm going to label 3 of them as protons. It doesn't really matter where they are, and 3 of them as neutrons. So 3 of each. 3 protons, 3 neutrons. And I'm going to do the same over here. And again, I'm going to draw these fairly large, but only 5 circles this time because I have 3 protons. But in this case, we're going to not draw 5. We're going to draw 1, 2, 3, 4, 5, 6, 7. This one's got an extra neutron. So 7 circles in all. Still 3 of them are protons, but now 4 of them are neutrons. And just so that they have been drawn here a little bit more normally, we're going to also draw some electrons flying around here. There's the electrons in their electron cloud, and I'm just going to draw the model of the atom that shows them sort of orbiting the nucleus in a undefined way, and label these as E- for electrons. And I've drawn 3 electrons around each atom, suggesting that they're neutral lithium atoms. But the difference between these 2 atoms of lithium really lies in their mass. We're going to name these by naming this one lithium 6, where 6 is what we'll learn is called the mass number, and we're going to name this one lithium 7. And these are the 2 common isotopes of lithium, or the 2 naturally occurring isotopes of lithium. Other ways that chemists describe the difference between these 2 isotopes is writing what we call a nuclear symbol. And the symbol is going to have the mass number, the number of protons and neutrons added together, written as a superscript to the left of the element, and the atomic number to the bottom right as a subscript. So this would have a mass number of 6 and an atomic number of 3. And over here, lithium 7 has a mass number of 7 and an atomic number of 3. So those are 2 common isotopes of lithium, or 2 naturally occurring isotopes of lithium, I should say. And notice that the atomic number we've already learned is given the symbol Z. And for both of these, Z equals 3, because if it didn't, then we wouldn't be talking about lithium. But we're now going to learn about a new symbol. The letter for mass number is A, and it is the number of protons and neutrons added together. And you may wonder why we've chosen such horrible letters for atomic number and mass number, respectively. Couldn't we call them A and M? Well, we're thinking in English, and this comes from the German Zahl and Atommass, which means count. In other words, the number of protons and atom's mass. And so we're going to have to get used to these symbols. I typically don't use the symbol A when I'm talking about mass number, and instead I will just write the words mass number, but we should define this in our notes. The mass number, which is given the symbol A, is the number of protons plus the number of neutrons. So if we take protons and neutrons and add it together, we'll always have a whole number because it's just a counting number of these particles. So the mass number, which is given the symbol A, is number of protons plus number of neutrons added together. We'll always have a whole number. As you can see, there's 2 different ways of naming an isotope. We could write its name or we could write its symbol, or 2 different ways of specifying an isotope. So I also want to clarify that and include something in our notes about that. We'll do that by putting one more example here. The example we'll give is that of potassium. Specifically, we'll talk about a potassium 40 atom. And we're going to write the symbol K. And then up here, we're going to write the mass number. And down here, we're going to write the atomic number. And of course, it may seem redundant to do this, right? If it's potassium, then of course it has 19 protons. Otherwise, it wouldn't be potassium. So why do we set it up like this? Well, this way, the mass number minus the atomic number can be sort of thought of as a subtraction problem that's ready to go here to give us the number of neutrons. And so this will also be a helpful formula for us to have in our notes. And I'm going to write note. If I take if I take A, the mass number, minus the atomic number, then I get the number of neutrons. So mass number minus atomic number is going to give you the number of neutrons. In this case, 40 minus 19, 21 neutrons. Let's do two practice problems. Write the nuclear symbol for these elements. For number one, I'd like you to write the nuclear symbol for an element that has a mass number of 78 and an atomic number of 34. And for the second example, we'll look at an element that has 91 protons and the number of neutrons is 140. So see if you can write the full nuclear symbol for these two elements. So there's the answer to those two problems. Important also to sometimes be able to tell the number of neutrons and recognize that would be, in this case, 78 minus 34 is 44 neutrons in this isotope of selenium. We'd call it selenium-78. This would be protactinium-231. So you might notice that when you look at the periodic table, we don't see mass numbers written because there are different isotopes of a particular element, and some of them are more abundant than others. So if you look at protactinium on the periodic table, you don't see 231 written there, and for many elements, you see a number in addition to the atomic number. You see another number called the average atomic mass, and we need to be careful to distinguish average atomic mass from mass number. Mass number, we've just learned, is the number of protons and neutrons added together for one particular isotope of an element. But we want to distinguish that from what we're going to discuss next, which is average atomic mass. Let's define this important term, average atomic mass. The average atomic mass is a weighted average. So I'm going to start this definition by writing the weighted average. And that's an important part of the definition, and that's because it's weighted by abundance, a relative abundance in nature of a particular isotope, so that more common isotopes are going to have a greater effect than other less common isotopes. It's the weighted average of all naturally occurring isotopes. Of an element. So more common isotopes are going to have a greater effect than less common isotopes. And we can go look at a few examples. Here's an example showing the natural abundance of different isotopes of lithium. So lithium-6 you can see is far less common. In other words, if we took a sample of lithium from the Earth's surface, from a lithium mine somewhere, then we'd see that lithium-7 is far more abundant. As a matter of fact, about 92.41% of lithium atoms are lithium-7, while only 7 or 8% are lithium-6. So the average atomic mass of lithium can be calculated as a weighted average. And I want to spend a little bit of time talking about the units of average atomic mass before we talk about how to calculate a weighted average. So I'm going to put an asterisk next to weighted average to come back to that point later. and instead introduce another important idea, which are the units for average atomic mass. The units for average atomic mass, or the units for atomic mass, are called atomic mass units. Let's define those. The atomic mass unit, and the abbreviation is the AMU, is used because using grams is simply not convenient. The mass of an atom in grams would be a ridiculously small number. So instead, we've invented a new unit of mass called the atomic mass unit. And the symbol for this quantity, or for this unit, is the AMU, or sometimes it's just written as a lowercase letter u. And we're going to define it just like a gram has to be defined or standardized. The AMU is defined in terms of 1/12 the mass of a carbon-12 atom. So why would we define the AMU as 1/12 the mass of a carbon-12 atom? Well, I'll go ahead and finish writing the nuclear symbol for carbon-12 by adding the atomic number there. Remember that carbon-12 is going to have 6 protons and 6 neutrons. And since protons and neutrons have about the same mass, that means 1/12 of the mass of a carbon-12 atom is basically the mass of a proton or a neutron. So I think that's a helpful thing for us to write down. That's sort of the spirit of this definition. We happen to use carbon-12 as a reference, but really the concept that this definition tries to approximate is the mass of a proton or the mass of a neutron. And this makes it pretty helpful if we want to estimate the mass of an atom. For instance, a carbon-12 atom will weigh about 12 AMU. A magnesium-25 atom will weigh about 25 AMU. And a uranium-238 atom will weigh about 238 AMU. Finally, let's talk about how we're going to calculate a weighted average. And when we calculate a weighted average, that weighted average calculation can be thought of this way. I'll show one practice problem here after showing the general strategy. We'll write weighted average calculation, which is what we had put an asterisk next to earlier. And we're going to, in order to calculate a weighted average, need to multiply each element's or each isotope's mass by its relative abundance. So we're going to take the isotope abundance, we're going to multiply by the isotope mass, and then I'm going to add that to the next isotope's abundance, multiplied by the next isotope's mass. And we're going to continue to do this until we have accounted for all of the naturally occurring isotopes. When we add those products together, then we will have the average atomic mass. So we'll do an example in just a moment. Notice when I talk about the isotope's abundance, then that's often going to be given as a percent, and you can use the abundance as a percentage, but then we'll have to divide our average atomic mass by 100 when we're done. Alternatively, you can convert all those percentages to decimal form, and then the calculation will be maybe a little bit more straightforward. I'll give an example first of lithium. And we're going to give that example by looking back at the data from that image before. Here it is. We have 7.59% of lithium atoms being lithium-6 and 92.41% of atoms being lithium-7. Well, let's see. I would take that data and plug it in like this. The isotope abundance will start with the more common isotope, which was 92.41% of lithium atoms, and I'm going to multiply it by the mass of that isotope of lithium. And I'm going to include a more precise mass of lithium atoms than you might imagine. You might assume that the lithium atoms have a mass of exactly 7. However, there's a reason why the mass is not exactly 7. So I'm including this data here, and I'll explain why the actual mass of atoms deviates a little bit more from their mass number than you might expect. But this is the mass of a lithium 7 atom. And then I'm going to add that to the next isotope, which is naturally occurring. And only 7.59% of lithium atoms are lithium 6. Lithium 6, it turns out, has a mass of 6.015 AMU. And again, you may wonder, why doesn't lithium 6 weigh 6? And why doesn't lithium 7 weigh 7? And before I explain that lithium 6 has a mass of approximately 6 AMU, and lithium 7 has a mass of approximately 7 AMU. And we won't get into the reasons for those differences until we study nuclear chemistry. But for now, suffice it to say that we need to use the actual mass of these isotopes, not their approximate mass. Now, when I calculate this and I add everything together, I get 694. Well, that's because I use percentages. And because I use percentages and not decimal forms of percentages or fractional compositions, I'm going to need to divide my final answer by 100. If instead you use the isotope abundances in their decimal form, so for instance, if I had done 0.9241 and 0.0759, then I would get my answer right away as an average atomic mass of 6.94. And on some periodic tables, it may appear as 6.941 because some of these digits are given to more significant figures. But you'll notice here I only had 3 significant figures with this percent abundance, so I'm only going to include 3 significant figures in my final answer. That unit is in AMU, and it matches what's on the periodic table. Now, you may be asked to do calculations like this and think to yourself, well, wouldn't I just look at the periodic table? The answer is right there. And it's true if you were really given natural abundances. But the way we'll practice this is by being given the abundances in a particular sample. And that can actually be a useful tool for chemists to use. An example has to do with how geologists can determine whether or not different lava flows originate from the same magma chamber, for instance. So we'll do one more practice problem of calculating average atomic mass. This practice problem involves chlorine. See if you can use the strategy we just discussed to solve this problem. What's the average atomic mass of chlorine according to this data? And here's the solution to that calculation. Notice in this case that I used the abundances converted from percentages to their decimal form. In other words, fractional composition here. Instead of multiplying by 24.23%, I multiplied by 0.2423. That way I didn't have to divide by 100 in the final answer.